Welcome everybody. This is Chester Chen. I'm the organizer, one of the organizers for San Francisco Big Analytics. So before we get started with today's two talks, and I want to just give you 30 seconds, go over some of the additional meetups we've planned. So the September 3rd, this is actually from Bill's AI Camps conferences, the Auto ML Global Summit listed here. And AICAM is one of our partners who provide the Zoom's videos for us. So and after that, we have a LinkedIn talk on the shuffle services, and you probably want to interest in that as well. So let me see all the other planned ones. So and then I believe AICAM have another. Sorry, so I thought you had another one. Maybe it was already passed. So there's two more events we planned, but I haven't really announced. One is related to IoT type framework, and then the other one is we're talking to on Apache Flight, and that's another open source framework and for fast transfer data. So we're talking them. I haven't announced that. Today we got two exciting talks, and one from Jason Toy, who's the COO of the Cloud app, and he's been very experienced in the machine learning world. He's talking about today's talk and this talk here. So on the NLP related topic, so the bootstrapping meaning with embedded language learning. So the other talk coming from Wander, who's the manager at Cloudera. So he's going to talk about the Apache submarine projects. So without further ado, Jason, please. Stop sharing here. How do I stop sharing? Jason, your turn. You can share your screen. Okay.
Yeah. Can you see my screen?
Yes.
Great. Yeah. So thanks everyone. I'm going to give a brief intro to bootstrapping meaning with grounded language learning and embodied cognition. So just very briefly about me, I've been doing mostly startup stuff, but in my free time, essentially, I consider myself. I've been doing a lot of applied machine learning, and then also some research trying to figure out like better implementations of basically neuroscience and machine learning, combining that to get better representations of learning. And I've worked with a few different labs that are trying to do things with bodies and touch, etc. So yeah, I want to basically just start off, just talk about how NLP has been doing the past 10 years. So obviously, thanks to deep learning and all the progress we've been making in machine learning, we've had great progress. There's a lot of very interesting models coming out. I think probably most of you are all familiar with the word tovec, famous for being able to essentially give a corpus of text, and in an unsupervised manner, it will create a representation that learns that text, which is essentially like a lookup table. It's a neural network that's a lookup table that stores a representation of all the words that are near each word for every single word. So the size of the corpus is n words, and so it's a matrix, is a n by n matrix of every word. So that came out almost 7 years ago. Then we've had transformers, which those are famous for essentially you can train the models. You can cut up the pieces of training and do the order out of order. So that means what the end result is that you can train in parallel, and which means you train it much faster, right? And then BERT, which came out 2 years ago, one of the main contributions there is that it's bidirectional, which means that what the end result is that you get much higher accuracy because it's training both going forward and going backwards. And then from that, we've got GPT-3, GPT-1, 2, and 3, which is a transformer. I'm not sure if it's BERT or not, but it's a transformer-based model. And one of the main contributions to that with that is that, you know, they trained it off 175 billion parameters, which is like the largest language model ever trained. GPT-2, which was the previous one, you know, it was 1.5 billion, so over order of magnitude more data. And there's already talks about what a GPT-4 may look like. I don't even know if there's enough data, public data, to train off of that. So, you know, we're making all this great progress. You know, you can feed in text to these models, and they can predict out new words. They can generate stories. I don't know if all of you have had time to play with it, but really amazing stuff. If you play with it, you know, it's not a but there's, you know, it makes a lot of funky, weird errors, and you can see it if you just try testing it though. So you can use GPT-3 as like a model, a Q&A model, where you give it a question, you get an answer back as well. So, you know, in these examples here, you know, we gave it we gave it some questions. Which is heavier, a toaster or a pencil? So it came back, a pencil is heavier than a toaster. You know, I don't know where it got that from, but it obviously, it didn't, I guess it just doesn't have the concept of what toasters and pencils are, because, you know, in most cases, a toaster is always going to be heavier, right? Another example, would an umbrella work if you were underwater? It answers no, because the umbrella isn't wide enough at the bottom to stop water getting in. So in this one, it seems like maybe I don't know, it just doesn't understand what those concepts are, because you know, there's no umbrella wide enough. You know, I don't know what happened there. Next one. Yesterday I dropped my clothes off at the dry cleaners and I've yet to pick them up. Where are my clothes? I don't think it even understood the answer. It said, I have a lot of clothes, right? So yeah, I don't think it understood it didn't understand the question. It just answered with something completely random. So this list goes on and on. If you feed it, if you try to like probe what its knowledge is, you know, many things it will get right, because it's just regurgitating what it sees on online, what it learned from its training data. But if you try to probe and try to get questions to like fundamental answers, basic things, not fundamental, but just really basic things, you know, you'll see it just doesn't have a concept of these things, and so it's going to answer incorrectly very often. So, well, why is that? You know, maybe it's because it's learning from text. I don't know. But so what is the text it's learning from? So it's mainly, well, I don't know if you're all familiar with Common Crawl, but Common Crawl is a copy, essentially. It's an open source nonprofit copy of the internet, like Google, but in a nonprofit. It's also taking Wikipedia, a bunch of other data sources, Reddit, and so it's got all these forums and stuff. So a lot of these data sources could be considered good and bad. Good because it is like real world data, bad because, you know, a lot of stuff on the internet can sometimes, especially on forums, be kind of trashy, right? But because it's only text and data, you know, this text that we write, it's essentially a single modality. So what is modality? Well, you know, modality meaning like sensory input. So it's only text, versus like if you look at any kind of like living creature or humans or whatever, we're taking in, even before we even learn how to read text, we're taking in vision, we're taking in touch, sense, smell, touch, hearing, all these different things to build up a model of our world. You know, model of the world, you know, concepts, all these things. And basically it's interacting with our world, right? And opposed to a text model, you know, most text models are usually meant to, especially these deep learning models, they're usually created to predict the next word in the sentence, but you can also train them for other things like classification of sentiment. Does this sentence, you know, is it good or bad? So this text, it's great because learning from text is great because we got so much of it. But if you only have text, my proposal to all of you listening is that text, if you only have text, it's just not enough. There's no interaction, and interaction, you know, I'm going to propose is key to the world, to learning, to building more intelligent machines. Um, so I want to just go into like what is meaning? What are these where does meaning come from? And how do we interact with these concepts, with meaning and these concepts, and then how do we represent them? Usually with symbols and words. Symbols is something we use in computers all the time, and can we represent the same symbols in computers that we do with how humans use symbols? So I want to just show this quote. I don't know if any of you know this guy. His name is John Locke. He was a scientist and philosopher born almost 400 years ago. And the quote from him is, "An unknown but potentially large fraction of animal and human intelligence is a direct consequence of the perceptual and physical richness of our environment and is unlikely to arise without it." So this is a scientist who was born almost 400 years ago. This is before we had electricity, computer science, machine learning, computers. I said, even machines, like the first machines with steam engines and all that stuff. All before that, and he's trying to figure out like where's this intelligence coming from, and his answer back then was that, well, he's not exactly sure where, but a large portion of it is coming from the physical richness of our environment and perceptions. What is perceptions? That is our senses interacting with the environment. And so I want to, this is a long time ago, 400 years ago, but I want to basically state or hypothesize that it's true. And we're a lot further now. We have computers. We can do very, very quick experiments, very big experiments to kind of know that. And we don't even need computers to know a lot of that. If you look at like children, how they interact with the world before they even know like a single word or symbols, they're already learning concepts, even though they don't know how to say the concept. So babies, like if you've watched a baby at a few months old, whether some of them we're still trying to understand if it's innate, if they're born with it, or if they learned it, but they already have a concept of heights and pain from falling from those heights, right? And you see babies, they're playing, if you give them blocks, for example, you give them different textures, they learn very quickly that there are blocks that are heavier, that are different textures that bounce. There's hard textures like the wood of a block. There's sharp edges. There's plastic, and then you can lift them up. It takes weight. These are all concepts that they learn, even though they don't know the word yet. But they're all from interacting with their bodies and the world. And so I want to give you some more examples of that. I want to show you words coming, like I want to show you some examples of words that are really based off of physical interactions with our world. So heavy, for example, the definition, these are all definitions that I pulled from the dictionary. Heavy, of great weight. Soft, easy to mold, cut, compress, or fold, not hard or firm to the touch. Push, to exert force on something. Ascend, to rise through the air. So all these words, I mean, I chose these words, but if you take any word from the dictionary, my hypothesis is that basically every single word, even abstract words like I, you, or homework, they all have a physical basis that are learned. All these definitions are coming from these physical basis, even before we're learning these other words. So like heavy and soft, all these words I gave here, these are all you have to interact and have a body to really know where what these mean. So all these words. So I gave a couple of words, but I just grabbed other random words. Hard, hard has a connotation. Like if it's hard, if something is hard, it's going to be probably heavier. It's going to be like difficult to break down because it's actually physically hard. Smooth versus smooth, it's like, you have a mental representation. It's well, smooth, it's like easy to glide across, for example. All these words, if you just look up the word in the dictionary, like a computer does now, it's a lookup table. I'm saying that you're not going to be able to get a definition from that. And that keeps growing to bigger and bigger concepts. Like nimble as a cat, this is not a word in the dictionary, but it's a concept that you hear. And what does that mean? Well, you saw cats, you may have a cat, you see a cat kind of like fly through the air or fall off something, it will still land safely because nimble means like able to like land. No, it doesn't mean to land, but to move quickly and in ways you want to move to keep yourself safe, right? So now I want to give a more concrete or different example, but from a different angle. So I don't know if you all know who Helen Keller is. She's famous for living almost her whole life as a blind and deaf person. So, we typically say we have 5 senses: touch, smell, hearing, sight, and sound. And so she was born she was born in the 1800s. And then around like a year and a half old, she lost her sense of vision and hearing. So she was deaf and blind. And but even with those physical disabilities, she became a very productive member of society. She wrote many books, and her books are amazing, by the way. So the picture on the right is a picture. The girl all the way on the right is her, and then on the picture, and then right next to her is her teacher, and then the picture on the left is the movie of her. But what the picture in the movie, the picture on the left is showing is when she the first concept she learned, they were trying to teach her how to like that the words, that concept had symbols, and the first concept they were trying to teach her was water. So what they did was they kept putting water on her hand. They would pour the water on her hand, and then they would write the symbol, whatever it was, W maybe. They would write W, and it took a while, but eventually she figured it out. She said, "Oh, these concepts have symbols for them," and after she learned that there were symbols for concepts, she was ecstatic. She went crazy because she wanted to learn every single symbol for concepts. And the reason why she explained in her book was because she wanted to learn the symbol for the concept of this. Every few nights, her family would open up this cold machine where these frozen objects were in it, and then she would feel the cold air, and then she would get something in her mouth. It was really hot outside. It was cold. That was ice cream. She wanted to learn the symbol for ice cream so that she could just write it and get it from her parents. So that was her main motivation. But then she talks about in her books, they taught her what the symbol for I was. So that, that was a revelation to her, because she learned that I am this entity separate. I'm in this physical world who has my own thoughts and my own mind, and I can interact with the world, and no one can, this is my world versus the external world. And so that was a very big revelation for her. She talks about how she learned, how she describes words in her mind. So one of the most interesting words. So she described the meaning of the word reliable. So reliable, what is reliable to you? It's reliable definition is, it has multiple definitions, but it's like getting something done that you said you were going to do, for example. Her in her mind, the definition is she runs her finger along the edge of a table, and it's a straight line running across something, versus something that's unreliable. I ask a colleague, hey, can you give me the report by tomorrow 5 p.m. Basically going from point A to point B, right? And instead, he says, yes, I'm going to do it. But instead, what happens is he takes a nap, he calls in sick tomorrow, and then a week later, he gives me the report. So he went in all these other directions before he got to point B. So unreliable, right? And so when I heard that definition of it, it just made me think, there's got to be a better representation of how we store symbols for computers than how we're doing it now, which is like, bag of words and word to vec models, where big lookup tables of similar words. That list of words I just showed you, a couple slides ago, many words have multiple definitions, but I showed you the original, the physical first versions of definitions we learned for words. I said heavy was of great weight, but all those same words, we use those words to describe, they have other meanings that describe other things. Like, so I'll give you the other definitions now. So heavy, describing a difficult situation. I live, I don't actually, as just an example, I live near the fires that are happening now, and I got evacuated, and I'm afraid my house is going to burn down. Someone could say I'm in I'm in a heavy situation. And why is that? Why do we use heavy there? Well, it could be it's still a weight on top of you. It gives you it gives you discomfort, and so it's still heavy, right? Soft. Another definition is it's lenient. My son, I want to have him do his homework to hand it in by tomorrow. He didn't do his homework, and so I was going to punish him. Instead, I gave him ice cream. I was too lenient. I was too soft. I didn't push him to finish the thing. Push also, push, the example I gave was to exert physical force. Push, has other meanings where, you force someone to a situation. I tried to push my colleague to finish the report, but he didn't do it. Even with trying to exert some not physical, but maybe it's like mental force on him or verbal force, I still was not able to exert the force to have him complete it. And then ascend, the example I gave earlier, the definition was to move up through the air. Well, it also, ascending, when you're moving up through the air, that has also a connotation of going against gravity, so it's harder work. I was a farmer 20 years ago, and I learned to program, and I moved to Palo Alto, and I ascended many social classes. So, all these words, assumption and hypothesis I'm saying to all of you is that every single word, not just as the examples I showed you, are coming from a physical basis of interacting with our world. And so we build these mental constructs from the basic interactions, but more and more abstract things are still built on top of these words, and they all have a physical basis in our world. As opposed to, word to vec, where I talked, we talked about it a minute ago, but the overall concept with the high level concept of word to vec, right? I was saying earlier, it takes the corpus, and it creates an entry for every single one of those words. And so, for example, for dog, it's gonna have a huge vector of zeros to ones, where 0 means it's the words it's not near it, and 1 meaning it's very near it. And so dog is probably gonna have a 1 for fur and hair and leg. But if I want to go understand, okay, well, what do those mean? I go to 1, I go to hair, and then hair has all these other things. I look up that vector, and that vector is, it has words like, I don't know, scissors and fur again, and skin, and if I look up tail, it has cat and dog and animal next to it. And so essentially it's a big lookup table it's like a merry-go-round, though, because it's going back, it's just going in circles. You look up one word, the definition is going to another word, and you keep going. And because these computer models, they don't have any other information. They're looking with Word to Vec, it's a big lookup table, and they're just going in circles essentially. Whereas with a human, and not just humans, with living creatures, our concepts are grounded in in this physical world. They're grounded in the physical world. We can take those meanings, and the meaning is derived from the physical world, is what I'm trying to say to you, versus, you know, this Word to Vec where, like I said, it's a merry-go-round. So, you know, why is it? What is it that human bodies potentially have? You know, this is a very active area of neuroscience research. So I just want to, you know, talk about that a little bit. You know, we don't know what it is yet, but some potential interesting properties of bodies, not just human bodies. I wrote human here, but it's actually every single living creature has most of these things. So proprioception, you know, proprioception is our body has a sense. We know where everything in our body is. So I move my hand. If I close my eyes, I move my hand up wherever it is. I know that my hand is in the upper right hand quadrant. I know I can feel that my leg is below me. Proprioception, an example of when you use it, you know, if you happen to you wake up in the middle of the night, you need to go to the bathroom, you can walk to your bathroom without like hurting yourself with the lights off all the way through, because you have a sense of where you're stepping. You have a mental model of where your bathroom is, and you can make it there without turning any light on. We have these things, we found these things called head direction cells in our brains. Anytime we turn, we have neurons that fire for a certain direction. We have 360 degrees. We've tested every single angle. We know that it fires for all angles. So, you know, we know that where we're looking, which is probably very tightly related to proprioception. And so this may be very relevant to how our bodies are, you know, some of the neurons we're using that may be applicable to artificial neural networks, right? Another very, very interesting property that we're just studying now. We've been studying for a few years, but so most of us, most of researchers believe that we store locations as egocentric. Egocentric meaning like I move in a direction, like if I'm trying to get from point A to B, I go a certain direction forward, and I turn, then from that position I go right and then left, up. In computer science terms, egocentric is the same thing as pathfinding. So the pathfinding algorithm, you know, you go from point A to point B by moving the object from self where it moves. Versus allocentric, we just in the past 10 years we've found this these cells that are allocentric, meaning that the cell's location, the object's locations are encoded from other objects. So what does that mean? So for example, this cup right here that I hold, we have mental models of the cup in our brain. Oh, sorry, you can't see it. So this cup, we have a mental model where the location of all the features of the cup, you know, I know that there's a base here, and from that base, I have a model that there's on the sides of the cup are the walls, and then at the top of the cup is the rim, and on the side, usually on the side of the cup, there can be a handle, right? And so those locations of those different features, parts of those objects are cup centric. So wherever there's a cup, I know that in general the cup is going to have these features around it. There's a lot of ongoing research that hypothesizes that maybe every single object that we learn about are encoded in an allocentric way. We found neurons that fire both allocentric and egocentric. So, you know, very interesting property. I want to talk about homeostasis just for very briefly, but homeostasis, I don't know if you know this term. This means keeping the body in a equilibrium, balanced way. Now, when we talk about the words like heavy, for example, heavy is something that, it's heavy because it has physical pain on you. If I put 1,000 pounds on any one of you, well, you'll probably die, but maybe let's try 500 pounds. You're going to be in pain. Your body does not want to be in that position where it has 500 pounds on it. It wants to be in an equilibrium where it's not hungry, it's not not hungry, not tired, not in danger, and in equilibrium. The temperature, our body, I forget what the exact number is, 98.3 or something like that. Our body is trying to maintain equilibrium, and so that's why we have things like pain, that like it's a signal saying, hey, get out of that pain situation. You don't want to be in that situation. And then we have skin. All our skin is basically our main interaction with our world. We have vision, and I would say most computer scientists probably think that vision is the main thing. I think that's completely wrong, especially if you look at someone like Helen Keller. Skin and these cells like proprioception and touch sensors, these are, I believe, the main sensor of what how the body interacts with the world. So, in saying all that, my hypothesis that I'm trying to share with all of you is that, to build better computers, we must get to systems that are integrating concept of body and worlds. So I don't know what that would look like. I've been thinking on and off about this problem for a couple of years. I don't know what that would look like, but I want to, I've been working on trying to create new representations of that. Something like, I don't know if it would be called body tovec, but like another representation that's similar to word tovec, where instead of the vectors that you get, the definition of a word is instead like some type of body representation. And so, what would be those features? I postulate maybe it's the body position, motion over time, because, all these concepts where everything is over time, as we're seeing, even when we do classification with just still images, how we make our models better is we take multiple pictures over different angles. And how do you get different angles of something? You move your eyes over time, right? So everything is over time. There's body involved in there somehow. How would you build this data set? Well, reinforcement learning is that is also state of the art. A lot of people are spending a lot of time in reinforcement learning, trying to build better models that interact with the world, right? Also, people do robots. I think robots are too hard. To build hardware and then to get the right sensors, the problem takes too long, and then the cost. So it's probably simulation. The problem, the big problem that with reinforcement learning, though, in simulation, though, is how do you create the right objective function? So there's all kinds of problems in this. Obviously, with objective functions, especially in reinforcement learning, you have to be able to train these systems in unsupervised manners, because adding supervision to, especially with deep learning, the data sets are too large. So I have been working on it a little bit, not too much. I just want to show you very quickly this project I've been working on. I call it ConceptNet, but it's basically, I took a child's dictionary. It's around 5,000 words. I scrubbed the data. Then I took all the data is the words, the definitions, part of speech, the examples, and then I wrote simulations in JavaScript. So they're generative, meaning like so these are simulations, but they also have physics in them. So this is the definition of leak. Leak is like accidentally lose or admit contents, especially liquid or gas through a hole. So they're generative, they have physics. Generative meaning like if I keep refreshing it, they change. It's open source. It's all in JavaScript. Here's just two examples. Here's descend, descending, moving, or falling downward motion. So yeah, that's just one thing I've been playing with, trying to build it. but you know, it's a toy project. So yeah, just in summary, you know, interacting with the world is a fundamental requirement of intelligence. And we are approaching the limits of what NLP can do with just text. You know, we're probably will get something like GPT-4 and 5, but the cracks are starting to appear. And if we want to take it to the next level, we must start to integrate some notion of a body into the training data and into the representation. And I don't know how that would look like. This is a very active area of research, but yeah, it needs to happen. And this is not like I showed you the example of John Locke from 400 years ago. More and more researchers now are moving towards this idea. I mean, it's been talked about for 30, 40 years in the cognitive neuroscience, but machine learning has been a big thing. It's been, you know, DeepMind, the CEO of DeepMind has been talking about this. They're spending a lot more money and time on grounded language learning. They have a bunch of very interesting research papers where they try to do grounded language learning. Yoshua Bengio, who's also done a lot of deep learning NLP, he just published a very good paper talking about why NLP is reaching the end soon because it's not incorporating this grounded language learning. So yeah. Oh, I have a link to that paper here. It's not my paper, but it's a really good paper just saying what's there. But yeah, that's basically the idea I want to share with all of you. And here's my contact info as well. Would love to go into any questions if anyone has any.
Great talk, Jason. So yeah, we'll get a few minutes, and anybody has questions, you can post to Q&A sections.
Do I, will you read it or should I find it or?
You can either way. So it's on Q&A section. So I mean, the questions right there. So, but I don't have any question at the moment. So
okay.
Yeah. Anybody has any questions for Jason on this topic?
Yeah. If not, you know, feel free to email me. But yeah, thank you.
Would you mind share the slides afterwards so I can share with the members?
Sure. Yeah. Wait, there's one. Is there?
Yeah. So there's somebody asking, what about?
Oh, yeah, metaphors. Yeah. So metaphors. Yeah, this is a very active area of research as well. Metaphors. You know, metaphors. Basically, you know, I don't know if you guys are all familiar with Douglas Hofstadter. He, you know, his work actually, in some of the research that I mentioned in here, Douglas Hofstadter's work is also referenced a lot. He believes, so Douglas Hofstadter, he's a cognitive neuroscientist and computer scientist who talks about metaphors. And he believes that metaphors and analogies is the core of intelligence. I think it probably is as well. But that's like, I think it's another parallel. So basically, you know, when I was giving those examples of, you know, I went to heavy, soft, push, and ascend. I gave the physical descriptions of these words, but they also have metaphorical words, you know, words that are related but have different meanings. And so, yeah, there's a lot of research. This, you know, I would call that research. There's a whole, it's called like language theory, language of mind. How do you represent words, concepts in a way that can jump between, you know, you suppress different features. So for example, the concept of a wave, right? A wave, you know, the physical representation is this thing that waves, right? But wave, you know, they took that same concept and in science, they use the concept of wave to represent sonar, to represent the actual wave, to represent things that are coming in waves, right? Like where it peaks and then stops and peaks and stops. So why I say that, you know, people are trying to figure out how to do that. And I think it is tightly related to this. That I would think is more on the algorithmic side of how do you how do you jump between concepts versus the actual concept. So I think it's two pieces. You store the concept somewhere, and there's some representation which I'm saying is probably a physical based way, and then it's how you jump between those concepts. So metaphors is very key. This is DeepMind, once again, they're spending a lot of time. They're doing broad research across many different areas of machine learning, but definitely metaphors is one of them. Grounded language learning and concepts, how to represent them. But I think they're tightly related. So yeah, that's my answer on that.
There's two more comments and plus one questions, and a pretty long question. So you want probably just give direct answer instead of I'm reading it.
Yeah. So I'll just set the one question part. So computer models, in order for computer models to understand the concept of heavy, they would need to be able to sense gravity's effects on objects. What are your thoughts on this? So yeah, I glossed over it because I only had, it was a short talk, but robots, I'm trying to find a slide. Robots versus simulation. So really, the only way for us to do it, so obviously we have to keep learning from neuroscience and grab as much learning as we can. Demis Hassab, from the CEO of DeepMind, he posted a paper a couple of years ago, 2 years ago, I think. One of the main things he wants to see happen is a lot more cross-pollination between computer science and neuroscience groups. I agree 100%. We have to take those ideas because those are the only places we know where intelligent machines work, right? But besides that, though, simulation, I think, is the only way we can make progress on it, because with simulation, even though the model, all models are wrong, but some are powerful, some are useful to us. At least with simulation, we can say, oh, well, I think we can probably simulate gravity in a way that's good enough for a computer to understand it. So I would say we want to use simulation to do that. It would be too hard to do in a robot, though, because we'd say, oh, let's try building it this way, and we find out, oh, actually, it's wrong. So then we have to go spend another 2 years prototyping a new hardware model to do that. So as a computer scientist, and I think that I speak for probably most computer scientists, we assume that simulations are good enough to represent the phenomenon. And this is always a debate in computer science. Does simulating a fire cause a fire? No, it doesn't. But is there enough learning in the system that it can, learn the cause and effects of a fire? So I think there's enough information that we can simulate things like heavy and gravity with simulation.
Great, great. I think we also run out of time, so thank you so much, Jason. So it's a great talk.
Thank you.